Hello, it's Professor Bedrero, and we're back. We're learning about the diagonalization of matrices, section 6.2. So one of the cool things about eigenvalues, eigenvectors, is the nifty things you can do with them. And sometimes we can diagonalize a square matrix. We'll talk about that a little bit later. So let me talk about the summary of our work from last section. So we had the A matrix of 1, 2, 3, -4, and he had eigenvalue of 2 with an eigenvector of 2, 1. And another eigenvalue of -5 with a corresponding eigenvector of -1, 3. Matrix C was also 2 by 2 of 3, 2, 0, and 3. He had two eigenvalues of 3, but only one eigenvector, 1, 0. Matrix M, 3, 0, 0, -2, 4, 2, -2, 1, 5, had two eigenvalues that were 3 and two corresponding eigenvectors of 1, 0, 1 and 1, 2, 0, and a third eigenvalue of 6 with his corresponding eigenvector of 0, 1, 1. So what do we notice about the results above? Well, sometimes our matrix has as many eigenvectors as the size, but other times he doesn't. Let's write that down. I'll pause the video here for a second to do that. Okay, so here's the cool thing that we can do is let's take our P matrix, or let's make a P matrix using the eigenvectors of A as columns. So I'm going to take these guys, and just since they're already in that order, I will use 2, 1 as the first column and -1, 3 as the second column. And let's find the inverse matrix P inverse, if possible. Well, we could do a quick check using the determinant. So that's 6 minus a -1, which is 7. So yes, matrix has to be invertible. And so we could do P inverse would be 1 over 7 times, switch the signs on these guys. Okay. Now, I think it's fun, but just for fun, I want you to do P inverse times A times P. So in other words, 3/7 times, or sorry, 3/7, 1/7, -1/7, 2/7 times the A matrix of 1, 2, 3, -4, and the P matrix of 2, -1, 1, 3. And I'm going to go ahead and put this into my calculator. So I've put into the calculator the A matrix is A, but let me move this up so you can see it. I put the P matrix in B, and so you can see him there. So I'm going to do B, or P inverse, times matrix A times matrix B, which is going to stand in for matrix P. And when we do that, we get 2 -1e -13. That's basically 0. That number's so tiny, it's in super scientific notation. 0, -5. So we get 2, 0, 0, -5. And why is that special? What's the relationship here? I'll give you a second to think about that. Hopefully you noticed that the 2 and the -5 were the eigenvalues, and they are along the diagonal of a square, or sorry, a diagonal matrix. Okay, so when we did P inverse AP, where P was the eigenvectors, we got back the diagonal matrix, and the diagonal matrix, the entries were the eigenvalues. Pretty spiffy. So what I want you to do now is make a Q matrix by rearranging the columns of P. Well, since there's only 2 columns, there's only one way to do that. So the Q matrix will be in columns -1, 3 and 2, 1. And then I want you to find Q inverse AQ and tell me what you get. So we'll let you pause the video here for a second to compute that. Okay, we're back, and I had the calculator compute it, and you'll see that I get -5, 0, 0, 2, which again, the eigenvalues are along the diagonal of this diagonal matrix, but you'll notice that they switch places because when we first created the Q matrix, the eigenvector of -1, 3 corresponds to the eigenvalue of -5, and the eigenvector of 2, 1 corresponds to the eigenvalue of 2. So when we create this matrix here, so whatever eigenvalue we place his corresponding eigenvector here in the first column, the eigenvalue will occur in the corresponding column of the diagonal matrix. Okay, and so you'll see that here. So next up, we want to ask you if we can diagonalize matrix C. So taking this matrix C guy, can I turn him into a diagonal matrix using a P or Q matrix? In other words, can I do P inverse CP equals some diagonal matrix where this P doesn't have to be the same as the one we did above because I've changed from my A matrix to my C matrix. So I'll think about that and then tell me why or why not. Well, the correct answer is no, because if we try to make that P matrix, it won't be square. Okay. And because if I try to make a matrix out of his eigenvectors, I only get this guy, and there's no way that I can do this guy in this. He's not a square matrix, so he won't have an inverse. So let me pause the video right there, and we'll catch up on the next part of the problem. All right, so we saw that we could diagonalize matrix A, but not diagonalize matrix C. So sometimes you can diagonalize a square matrix and sometimes you can't. So how can we tell if a matrix is diagonalizable? And no, I'm not making that word up. That's an actual math word, diagonalizable. So the way to tell is if we have as many different eigenvectors, and by different I mean linearly independent, as the size of the square matrix. This is a 2 by 2, and we had 2 linearly independent eigenvectors, where C only had 1 eigenvector on a 2 by 2 matrix. Okay, so we'll let you write that in here. And now I'm going to pause and let you see if you can find a matrix P that will diagonalize matrix M, and then find P inverse MP using the information from the top of the page.